no. The tangent circle, not the unit tangent circle. So let's see if we could do a little bit of work on the side here and keep everything on one page. And we're not going to be able to, but let's just try. So let's find let's first recreate our equation or our vector function. So this is your parabola, y is equal to x squared, and then if you have y equals an f of x function, you can easily transform that to a parametric equation or a vector function, and then we could do stuff to it. So I think we found the unit tangent already, didn't we? Trying to skip some steps here. So we need to take the derivative, and then if we took the derivative, there's no prime here. Actually, I don't remember, so I'm just going to look back at our notes, because we have notes. Oh, we didn't do it. All right, so I guess we'll have to do it. So we'll need to backtrack a little bit. Well, not backtrack, but do the work that's involved here. So to find the unit tangent vector, we first need to find the derivative of the position, and then we need to find the magnitude of that. This seems like deja vu. We did do this, didn't we? Yeah. So the square root of each component squared added together. And then we want to just make this into a fraction. So the t is equal to this thing. I'm just going to write it as a fraction. But we can think about this as scalar multiplication also. So now we want to take the derivative of this. Ooh, man. What? No, that would be integrating, but we're not integrating. So derivative, there's going to be some chain rule here, but I think we want to use a product rule in general because it's a scalar times a vector. So, all right, this is going to get messy. T prime of t is equal to actually, before I do t prime of t, this thing needs its own page. Let's go to the next page. So I'm going to rewrite this as 1. Actually, I'm just going to write it as 1 plus 4t squared to the 1/2, negative 1/2, times a vector 1 comma 2t. So let's apply the scalar times a vector derivative. So if I want to take the derivative of this, it's the derivative of the scalar times a vector plus the scalar times the derivative of the vector. So just like the product rule. So negative 1/2, 1 plus 4t squared to the negative 3/2 times the derivative of the inside, which is 8t, So that's the derivative of the first times the second, and just keep the vector the same, plus the first times the derivative of the vector, so it's 0, 2. And then we're supposed to try to find the magnitude of this. Okay. So what we'll do is to find our, this is our end game. We want to find your normal vector evaluated at 1. So what that's equal to is I left some room here because I'm going to put in 1 to help us out a little bit, dealing with smaller things instead of this big whole thing. So the normal, remember, the unit normal is equal to the derivative of the unit tangent divided by the magnitude of the derivative of the unit tangent. And so here we have the unit tangent. We want it evaluated at 1. Sorry, I need to change this into 1. And I'm doing this so that we can look at what we've taken the derivative of with t prime and then just put 1 in there, and then we can come up with a normal vector for this one special case. So that's what we're going to do. We're going to this thing? Yeah, it'd be nice to simplify it. I don't know. I don't think so. Because especially for this applies to 3 dimensions also. And so that's what we're going to move to. All right, let's put 1 in there and let's see how simple it'll get. Let's see how things simplify. So this is gone. This is 4. 4 times 1, negative 4 over 5 to the 3 halves. Did I do that right? If I put 1 in for the first part? In for t? All right, you guys think about that. I'm going to keep going. Square root of 5 in the bottom, and then 0, 2. So I have negative 4 over 5 to the 3 halves, comma, negative 8 over 5 to the 3 halves, plus 0 and 2 over square root of 5. So let's see if we can combine everything here. The x's are, since it's 0, that makes it nice. And here, I don't know if we care about having common denominators to combine them, but I think if you have common denominators, you would multiply this by 5 over 5. So that's going to be 10 over 5 to the 3 halves. With the same denominator, I have 10 minus 8. So that becomes 2 over 5 to the 3 halves. So that gets our t prime at 1, evaluated at 1. And to make this into a unit vector, we just divide by its magnitude. So we find the magnitude of t prime of 1 is equal to the magnitude of this, which is the square root of 4 over 5 to the 3 halves squared plus 2 over 5 to the 3/2 squared. All right, well, they have the same denominator, so we can combine them. This would be square root of 16 plus 4 is 20 over 5 to the 3/2. That becomes 5/3 when you take 5 to the 3/2 squared. So there's a 5 in the 20, right? So the 5 and the 20 would cancel. That would leave you with 4. Square root of 4 is 2. It would cancel inside one of the 5s and one of the 5s, so that's 5 squared. And then under the square root is 2/5. Boy, is that right? So let's put this together, as in put it as a fraction or multiply it by the reciprocal or however you want to think about it. So n at 1 is equal to this thing. I'm going to take the reciprocal of the magnitude, so I'll have it as if I'm multiplying 5 over 2, and then 4, negative 4 over 5 to the 3/2, comma 2 over 5 to the 3/2. Let's see how this is going to work. 5s would cancel, so I have square root of 5 in the denominator. And 2s would cancel, so that will leave 1 on the y and then negative 2 in the x. So negative 2 over root 5 and 1 over root 5. Wow, that was a pain. Let's at least check that this is unit length. So square, add, should equal to 1. All right, we got ourselves a unit vector. So let's update our picture so far. We have our parabola. And we have the point at 1, when x is equal to 1. And then we just got this vector. It's going negative 2 in the x, positive 1 in the y. And it has unit length. That looks pretty perpendicular. So we have our tangent, unit tangent, and now we have just found our unit normal vector. Whew. So, what was our kappa again? What was it? Oh yeah, but I thought we computed it for this particular problem. Kappa was 2 over 5 to the 3/2 power, right? From last time. So what I want to do is I want to go to this point 1, 1. I want to scale my unit normal vector by 2 divided by 3, or 2 divided by 5 to the 3/2 power. And what that's going to do is that's going to give me a point somewhere, I don't know exactly where, so that's going to be the center of my circle that's tangent to the curve. Okay? So how am I going to get to this point? Multiply the reciprocal of the curvature. Remember, the radius is the reciprocal of the curvature. So if we multiply the reciprocal of the curvature by the normal vector, that's going to extend our normal vector. And then we just have to go start with 1, 1 and add that thing that we just found. And then that's going to get us to that point. So the point, go to 1, 1. That's R of 1. Go to that point 1, 1, then add the reciprocal of the curvature times your normal vector at 1. All right, let's see if we could do that. So 1 over kappa times -2 root 5, 1 over root 5. Actually, I'm going to erase 1 over kappa and actually put the value there, which is 5 to the 3/2 power divided by 2. All right. So 3/2 would cancel with 1/2, or the power of 3/2 would cancel with the power of 1/2. That will leave us with just 5 to the 1st power on the numerator. And then the same thing will happen, except there's a 5 here, right? Did I do that right? Yeah. I got 1 nod. And then let's add 1, 1 to it. It's getting to be a long page here. So 1, 1 plus minus 5, 5/2 is going to be equal to -4, comma 7/2. So that's my point. I hope that's right. So I have this point on my parabola. Now my unit tangent vector was -2 divided by square root of 5. And 1 over square root of 5. So that looks pretty normal. pretty perpendicular to the curve, right? And so now, if we extend this to this point, we're going to get the point -4 and 7/2. So this over here looks like it should be, this dot over here looks like this is going to be the center of my tangent circle, which looks reasonable because this is pretty flat, right? So let's actually draw the circle to see if we're correct. So the equation of the circle is x minus the x value squared plus y minus the y value squared is equal to the radius. What was the radius again? Five raised to the 3/2 divided by 2. That's your radius, and then we want to square it as part of the circle. All right? That looks pretty tangent, doesn't it? Let's zoom out a little bit. There we go. Tangent circle. So after class yesterday, I was kind of excited and thought, hey, this is kind of cool, tangent circles. So I wrote an example where we can actually follow through a tangent circle. As we change the point that we're on. Pretty cool, huh? So the way things work in math, if you just use symbols, then you can make it, you can change one little thing and then it'll follow the changes. So for example, if we want to, instead of using the x squared function, if for some reason we want to look at the sine function to see how the tangent circles work there, let's check it out. And tell me what you think happens to this tangent circle. So it gets smaller. What can you say about the curvature here? It's large. Remember the reciprocal. The curvature and the radius are reciprocals. Yeah, what do you think? Let's see. Let's just go to pi 3, 4. Let's just go to 4. So let's look at what happens. All right. So as your curvature gets flatter, it's the reciprocal, right? At some point, and maybe I should have told you this, but a straight line has a curvature of 0. So at some point here, the sine function is eventually going to have a 0 curvature. And you know what happens when you divide by 0? You go off to infinity. And what happens there is after you go off to infinity, there's this point where you switch, and that would be exactly at pi, where you switch concavities instead of going up, being concave up to concave down. And when you do that switch, your curvature goes to 0 because you have a straight line there. And then when you go past that, it comes back again. Pretty cool, huh? So this program has the function that you would define, and then it has a slider that you can change. But there's the curvature, and then I have to find the x and the y components of the point that we're going to get to. And so these are the x and y components of the normal vector, the unit normal vector. And after you do that, it's the 1 over the curvature times the normal vector. And then here's the circle right here. Okay? So if you guys want to mess around with this, if you have the program, you can mess around with this at home. If you don't have the program, you can go to the STEM Center and log on to one of those computers. This program is available here. You can download it from your notes and then take a look at it. All right? If you're interested. Since I did spend some time on it and wanted to share it with you all. You guys can look at it or not. All right. So that's curvature. And now we've introduced ourselves to the normal. So let's go and talk about the unit tangent vector and the unit normal vector. So I mentioned that this idea can be extended into 3 dimensions, and in fact, it's most useful in 3 dimensions when we talk about a 3-dimensional space. So let's say you have a drone, a robotic drone, autonomous, that's going out, flying somewhere, and it's trying to map out its terrain. Or better yet, your drone is trying to bomb something. Is that a good thing to do? Your drone is trying to shoot a basket somewhere, trying to hit a target with a ball, not a bomb. Okay? So your drone is flying out in space, and your drone is going to follow a path in space somewhere. So here's your straw drone with propellers, and let's say there's a target here, and let's say the target was a basketball hoop, and this drone is capable of firing in a straight line, right? So what your drone does at any point in time, whether your drone is at some point over here or at this point ready to shoot, what your drone does is it doesn't refer back to the origin as the starting point. Okay, it could, but a lot of times when it's moving around, a lot of the terrain changes or the origin, it has to rely on its own origin. So what the drone does is it follows a particular path. I'll keep my path in blue. And then what it's going to do is going to define a direction that it's moving toward. And that would be the tangent vector. Right? Now, it wants to know how to aim and propel this projectile to make it to the basket. So it needs coordinate systems. And so in doing so, you need to define like a three-dimensional frame from the drone's point of view. And we have one vector already, and that's the tangent vector, because that's the direction that the drone is moving. Now, based on our stuff that we were doing last time, we have a second vector, the unit normal vector. And that vector is perpendicular to the unit tangent vector. And so now, since you're flying in 3 dimensions, you need a 3-dimensional frame to define for yourself so that you can explore everything around you from that particular instant in that frame. And so there's a third vector that we want to get. And a very nice property for this vector would be, it would be really nice if this vector was perpendicular to both the t vector and the n vector, right? So we want this vector to be perpendicular to the t vector and the n vector. And it would be nice if it was also of unit length. Because now, if I want to look at this basket right here, I can use, I was going to say linear algebra, but I can use the combination of t, n, and what should we call this third vector? B, for binormal. So that if we're trying to shoot to this basket, we can say, well, maybe this basket is 2t plus, maybe I need to go negative 1/2 n, and then a minus minus 3b or something. So then that's an easy calculation for the drone to be able to do, and say, just based on where I am, I'm just going to set my projectile to be positive 2, negative 1/2, negative 3, and then shoot. And then from this point, assuming that this point is 0, 0, 0 at that instant, you should be able to shoot to the direction that you want to get at. So this is sometimes called the TNB frame. And named after some guy, Fernet. This is also sometimes called the Fernet frame. Matt? It just gives you a third dimension to your t and your n vectors. Binormal. Binormal. Normal. Normal. Yeah. So how we're going to get that? It's a cross product of those two vectors, and we'll write that out. Yeah.
Are any of those like the x, y, like do they all just flip around? So not.
Yeah. I mean, they have to move around.
Normal isn't always like the same.
No, because if your drone, you know, which way is this going? This drone is going this way now. If I'm following this path, at this point over here, I'm this way, and then my normal vector might be going this way, and so the unit binormal might be going that way. They're all perpendicular to each other.
And it's going that way based on where your tangent vector is.
Yes. Yeah. It actually is also, because the tangent is like the first derivative, and then the normal vector is the derivative of the tangent vector. So you're essentially looking at the acceleration, although it's not exactly the acceleration, but it's along the same plane of the acceleration. Because we took the unit normal vector, the tangent vector, we took the made into a unit vector, so now we don't have control over. Not necessarily, but it's in the same plane. Whoa. What? Okay. Okay. Let's see. Huh. Would more pictures on the screen help, you think? What am I looking for? I am looking for, oh, I know what. Maybe I'll just. So my function is kind of like that roller coaster. It's 2 cosine t, 2 sine t, and then I have a trig function that makes it go side to side. Now the big black vectors are just the axis. And as I move around, let's take those boxes out first. Where am I going to find them? U, T, P, T, T, N. All right. So the red vector is the tangent vector. And if you follow that going around, it's going in the direction of the path of the curve, right? The unit normal vector, UN, is green. And then the binormal vector is blue. And if you're colorblind, I'm sorry. So you see that as you go along the curve, the unit tangent is always going in the direction of the curve. Now, the other two vectors have to remain perpendicular, but they twist and turn depending on how the curve goes. Right? So as they twist and turn, if we focus on the unit normal vector, the normal vector is going to be pulling toward the acceleration. Okay, Will? Torque? No. Yeah, there's no, not quite, because it's the cross product of, so it's not that. They called it something. I forgot what they called it. So back to Joe's comment here. If we get rid of the binormal vector, guess I should have taken those out. Uh-oh. There's a comma. So these two vectors now, the red vector and the green vector, are just the tangent vectors and the normal vector. This is really a little bit more complicated than we probably should be looking at. Let's simplify our vector, our curve. Instead of doing this going around like that, let's just do a helix. So a helix, sine, cosine, and t. So let's do 0.2 times t. And let's make this go a little bit farther. Oh, I know what. I can just double the speed. So as you go up, because it's going around in a circle, essentially, you can imagine the acceleration just pulling towards pulling in. It's centrifugal force acceleration. So it's always going to go in. And you can see that the unit normal is always pointing in, and it doesn't fluctuate up or down. And if we were to throw the unit binormal, in this particular case, it's always pointing up. That's because your unit normal is just going in. So if your normal changes, then your binormal is going to have to change also.
So what is the direction of acceleration?
Because in this particular case, it is, because it's going inward. That's the direction of acceleration. So it's not necessarily in the direction of the acceleration, because the acceleration is not always perpendicular to the tangent. Okay, but it is on the same plane. I still want to say that because I want to talk about that plane, what that plane is. Harrison? No. So I'm going to, this is too thick. Let's change it to just 2. Now, if we introduce a plane that contains the tangent vector and the normal vector, that is the plane that contains the tangent vector and the acceleration. So that plane that you're seeing here is a plane that's being spanned by those two vectors, the first two vectors. Okay? Yeah? And the normal vector. The t and the n.
So the plane is formed by those two vectors.
One plane is formed by those two vectors. Okay? So the plane formed by these two vectors is the same plane where the regular tangent and the acceleration are on. Harrison?
Would the normal vector have a z coordinates for
Yeah, in this case, yeah. It's a helix, since it's a helix.
So the binomial wouldn't be exactly up
Yeah. If you imagine you're in this roller coaster, right? So, and then you're sitting straight up, then the binormal would be your spine in the back. And if you're going around in a circle making left turns, your normal vector is in the inside because that's where the acceleration is. And then you're moving forward, that's your tangent. So the plane that contains the acceleration vector and the tangent vector is going to be the same plane that contains the unit tangent and the unit normal vectors. And that plane is called an osculating plane. So let me, before we go on and get carried away with this, like I'm right now getting carried away because I'm getting too excited. Let's come back and try to remember all our formulas. We have the unit tangent vector defined by the derivative of the position, and you want it unit, so you divide by its magnitude. We're going to go formula hunting here. R is the position vector. Your normal vector, we found that the derivative of the unit tangent is perpendicular to the unit tangent. The derivative of the unit tangent is perpendicular to the unit tangent, and therefore that makes a good candidate for your normal vector. So we have t, and then we have n. And then, as Evan mentioned, the binormal vector has to be perpendicular to both the tangent vector and the normal vector, and so you would cross them. And it turned out that since the unit tangent and the unit normal are already unit vectors, they have length 1. When you cross two unit vectors, think about the area spanned by the parallelogram. When you cross those two unit vectors, then that cross product is also going to be a unit vector. So we don't need to divide by the magnitudes here because it's already a unit vector. So here are our three main vectors. And now each pair of these vectors, there's three vectors, so there's 1, 2, 3. So there's three possible planes we can look at. So the plane containing t and n is called the osculating plane. The plane containing n and b is called the normal plane. And then the other one doesn't really have a name. But there's something special about the osculating plane. So if you imagine you're in a roller coaster, right? You're going forward, that's your unit tangent vector, and your acceleration vector, whichever way your acceleration vector is pointing. So you're sitting in this roller coaster car, right? You're sitting on this roller coaster car, and then forward is the unit tangent. Your n vector is either to the left or to the right, depending on which way you're turning. So in a roller coaster, if you're turning left, then your n vector is on your left side. And then your b vector is your spine going up. Okay? Now your roller coaster goes up and goes down, and then turns, right? So your tangent, your normal, and your binormal vector are turning along with you. Okay? Now, the floor of your car, whatever you're sitting on, is the osculating plane. it contains your tangent vector and your normal vector. If your car has a back, that is your normal plane. It's perpendicular to the curve that you're on. And then the third plane would be your tangent and your binormal. Like I said, doesn't have a name. But those three planes create your three-dimensional space. Or actually, the three vectors are enough to create your three-dimensional space. So, you're probably reading down here the osculating plane and the osculating circle. What's the osculating circle? It's a circle that lies on the osculating plane, but it also is what? It's a tangent circle. So the tangent circle that we were looking at in 2 dimensions can be also explained in 3 dimensions. But in 3 dimensions, it's 3 dimensions, right? The circle is only a 2-dimensional thing. So we need to put that circle on a flat plane somewhere. And that flat plane contains the tangent vector and the normal vector, the tangent vector and the velocity vector. And it's on the osculating plane. Yeah? For fun geometry. The important part in the tangent circle, though, is the radius, which is the curvature, the reciprocal of the curvature. And the curvature is important because you're in a roller coaster, you got a really large curvature. That means you better be ready because it's going to be a sharp turn, right? And so if you're just going straight, then you have 0 curvature. And if you're going to have a sharp turn, then it's going to be a large curvature. And then the whole idea of going up and down is it's called something. It's not torque. Maybe it is torque. I have to look it up. Yeah.
The tangent circle is actually very relevant to things like graphic design. But I wanted to ask if there is a tangent sphere. Is that technically possible?
It's technically possible, but it wouldn't apply to curves. But if we start doing surfaces, you can think about a tangent sphere. Yeah, because it's 3-dimensional, right? So it has to be able to capture all the other stuff. But we're not going to do that.
Well, you did this in 4 dimensions.
Yeah, but then we're still looking at surfaces. We would look at 2-dimensional surfaces in 4 dimensions, and then you can define tangent spheres. So again, 4 dimensions isn't really something that you would be able to visualize, unless you get some aid and let go of some 3-dimensional tangible stuff and just go add another dimension to your life. But I didn't say that. They didn't hear me or see me. But yeah, I studied in Santa Cruz, so I saw some 4th dimension stuff there. So if we come back and take a look at this Mathematica representation, we have the osculating plane. Think about you in a roller coaster, in a car, the car in a roller coaster, and then the floor of that is the osculating plane. And remember, the direction you're moving is the tangent, and whichever way you're turning, left or right, is going to be your normal, and then your binormal is just going to have to be perpendicular. It's your spine going up and down. So we can also come back and put the 3 planes here. to set up our Fernet frame. And so from here, you can have yourself enclosed in this little box, and then just the direction that you're moving is going to be the direction that we're looking at. So let's change it back to where it's changing all the time. In our original picture, I think it was a cosine 4t or something. That's kind of like a Pringle, huh? So you see how it twists and turns as you go along this roller coaster, if you want to think about it as a roller coaster. And that determines the size of your frame. I'm trying to find a good view to take a picture and put in our notes. That looks good. So we can label these things. We have our tangent. We have, which one was our normal? The green one, right? Normal. And then the blue one is our binormal. And then the plane that has the tangent and the normal vector is the osculating plane. And then the normal and the binormal has the normal plane. So in terms of computing this, it's kind of like the stuff that we've been doing. You just need to take derivatives and then plug it into the formula, and the formulas are just here. So you take the derivative, divide by its magnitude, and then you take the derivative of the unit tangent, divide by its magnitude, and once you have that, you have the t and the n, you can just cross that to get b. I think you have one homework problem where you have to identify the three vectors. And then you have another homework problem where you have to look and match the graph and the unit, the tangent vectors, so that should be fun. All right, so we have a test. In the test, I usually allow people a sheet of notes. So you guys, if you want to start preparing a sheet of notes for the test, you can just start thinking about doing that this weekend. 2 sides, 8.5 by 11. And so put whatever you can that you want there. And then I'll have the review available sometime tomorrow. When we talk tomorrow, I'll let you know. And then the exam will be on Wednesday. All right? All right, see you guys. What? Because that's how it happened in the schedule.